So we found CD, so we're done. Okay, now we're going to get into what's called the perpendicular radii rule. Remember, radii is just the plural form of radius. So what is the perpendicular radii rule? This states that a radius that is perpendicular to a chord will always bisect the chord. Okay, so let's zoom in. What does that exactly mean? Well, first we have a chord, and let's remind ourselves what a radius is. Remember, it's the distance from the center, where this is our center, let's say it's B, from the center to any point on the circle, right? So it can be here to here, or it could be here to here, here to here. Those are all radii, and they're all going to be the same length. But we want a radius that is perpendicular to the chord. So this is our chord. So let's draw a radius that is perpendicular to it. So it would look like this. Oops. Like this. Not perfect, but okay. So let's call this D. And remember, it wouldn't be correct if you had it drawn like this. Let me do this. Oops, sorry. It's not correct if you draw it like this, because why? It is perpendicular, but it is not a radius, because remember, the radius is the distance from the center to a point on the circle, and this is not a point on the circle. That is a point on the chord. So make sure it should be drawn like this. And again, let's call it D. So again, BD is our radius, and it's perpendicular to the chord. So a radius that is perpendicular to a chord will always bisect the chord. What does that mean? Since the radius is perpendicular to the chord, then it will bisect the chord. So that means I should label this point. Let's call this E. It might be hard to see. That means segment AE is congruent to segment EC because the radius is bisecting this chord into two equal parts. So that is the perpendicular radii rule. So let's get into the proof of the perpendicular radii rule, okay? I'm going to choose a different color. So based on the figure, actually, let's back up. So let me remind you of what the perpendicular radii rule is. Remember, it states that a radius that is perpendicular to a chord will always bisect the chord. So when we're doing a proof, for this proof, we want to prove the last part. Will always bisect the chord. And remember, what does it mean to bisect the chord? It means we'll divide it into two equal parts. So we want to prove that segment AB is congruent to segment BC. That is what we're trying to prove for this rule. Okay, so that's our goal. We want to prove that segment AB is congruent to BC. So looking at the figure, what are we given? We're already given that segment ED is perpendicular to segment AC. How do you know that? Because you see that it meets at a right angle, so you know it's perpendicular. And this notation means perpendicular. So that is our statement, and we'll write given. Okay, what other statements can we make? Well, since we see that it is perpendicular, that means it meets at a right angle. So this is a right angle, and this is a right angle. So our second statement is angle DBA and angle DBC are 90 degrees. And what is the reason? How do we know that? Well, we know that because segment ED is perpendicular to segment EC. Okay? Now, what do we also notice? Well, what if we drew two new radii? Okay, remember radii can be like this or this, as long as it's from the center to any point on the circle. So what if we drew radii to connect these points? Right? So these are line segments connecting these 2 points, and they are actually radii because it's from the center to a point on the circle. So these are both radii. And what did we also know about radii? All the radii are equal because the distance from the center to a point on the circle is the same for all the points. So now we know that segment DA, which is a radius, is congruent to segment DC, which is also a radius. So what is our reasoning? Our reasoning is that radii must be congruent. Must be, congruent. So let's go ahead and write some hash marks to represent that in our figure. Okay, so now what else can we conclude? Well, we can conclude, what else? We want to try to find other things that are congruent to each other. So DB, we can say segment DB is congruent to itself. And this is the reflexive property. We see these a lot in proofs. And what does the reflexive property state? It states that any geometric object is congruent to itself, whether it's an angle or a segment. Okay, now what do you notice? Well, let me do hash marks first. This looks like side-side angle. Remember we said side-side angle was not a postulate that guarantees congruency, right? The postulates that did guarantee congruency were side-side-side, angle-side-angle, side-angle-side, and angle-angle-side, right? Where the side didn't have to be included. Here we have side-side angle where the angle is not included. And we said side-side angle didn't always guarantee congruency. But in this case, it's a right triangle. And we didn't go over this in previous videos, but since it's a right triangle, if two sides were congruent, then these two triangles are congruent. So we can conclude that triangle DBC is congruent to triangle DBA. And it's not the side-side angle postulate. We didn't go over it, but it's called the RSH postulate. You might see it be called something else. But it basically states that, what does this R mean? It stands for right triangle. Side means one side is congruent, and H means the hypotenuse are congruent. So since we have two sides congruent in both triangles, then both triangles are congruent. Okay, so we just proved that both triangles are congruent. But remember, our goal was to prove that AB is congruent to BC. Well, now we can, because remember, we can actually conclude that AB is congruent to segment BC. Why? Because remember, CPCTC. Sorry. What is that shorthand for? It stands for corresponding parts of congruent triangles are congruent. What does that mean? Parts that correspond to each other in two triangles, such as AB corresponds to BC. They correspond to each other, and these two are congruent triangles, and because they correspond to each other, then these are congruent. So we can conclude that AB is congruent to BC because they correspond to each other, and these two triangles are congruent to each other. So we just looked at the proof for the rule that we just learned. Okay, so again, let's remind ourselves of the perpendicular radii rule, and I drew some pictures. A radius that is perpendicular to a chord will always bisect the chord. So this states, if radius DE is perpendicular to chord AC, then it will bisect the chord. So that means segment AB is congruent to BC. We also know the converse is true. Remember, that is when we switch the constituents. So this is the first part of the statement. Radius is perpendicular to a chord. And the second part of the statement, always bisect the chord. So now we're going to switch it, and it will be called the converse statement. So this states that if a chord is bisected by a radius, then the radius is perpendicular. So if AB is congruent to BC, that means if it's bisected into two equal parts, then the radius is congruent to the chord. So the radius is, not congruent, then the radius is perpendicular to the chord. Okay, let's look at an example. This states, let's zoom in. This states segment AB. Now remember, you should be able to recognize that this is a radius because we're going from the center to a point on the circle. AB is perpendicular to CD. You should recognize that this is a chord because two endpoints are on the circle. So we're given that it's perpendicular, so why don't we draw a right angle. Yes. So now we want to know, what is the measure of CD? Well, according to the perpendicular radii rule, if the radius is perpendicular to the chord, then it will bisect the chord into two equal parts. So since we know that one part is 6, we know that the other part has to be 6 because it is in two equal parts. So what is the measure of CD? It's just 6 plus 6 equals 12, and let's just say centimeters. So the measure of CD is 12 centimeters. Let's look at another example. What is the measure of the radius? Okay, remember the radius is the distance from the center to any point on the circle. If we're given that this whole thing is 18, then we should be able to recognize that this is a diameter because two endpoints are on the circle and it contains the center, right? And what do we know about the diameter? We know that the diameter is 2 times the radius. So here's one radius, here's another radius. So if our diameter is 18, then our radius would just be half of it, would just be half of the diameter. So we know that the radius is 9. Now let's just say centimeters.